Welcome to the deep dive. Okay, so for months now, the noise has been pretty intense, hasn't it?
Oh, yeah, definitely.
All these headlines shouting about large language models, LLMs, achieving basically superhuman scores in competitive programming,
We're talking ELO ratings, supposedly above 2,700.
which is huge. That puts them above elite human grandmasters.
Yeah.
We're talking top 0.1% globally.
It's a really spectacular claim. And, if it's true, it changes a lot about how we think about AI capabilities.
But, as we always do here, when claims sound that good, well, you gotta check
Yeah.
the plumbing, right?
Exactly. First question, was the benchmark clean?
Yeah.
Was there contamination? Like models trained on the answers?
Or just flawed testing methods. That happens too.
It does.
So our mission today is to dig into that using some news source material. It's about a benchmark called LiveCodeBench Pro.
Right. And this one's different. It's been carefully curated, contamination-free, and the team who built it includes actual international Olympiad medalists.
So people who really know competitive programming inside and out, they designed it specifically for a fair fight.
And here's the spoiler, really the core finding from this LiveCodeBench Pro data,
Get ready for it.
these models. They still have really significant, measurable limits when you test them under proper contest conditions, without all of the external help.
Okay, so break that down. What did they find?
Well, take the best model they tested, this of 4 mini high. Without any external tools, it passed about 53.5% of the medium difficulty problems.
Okay, 53.5% on medium.
Yes.
That sounds respectable.
It's not bad, sure. But then you look at the hard problems, the ones rated over 3,000 ELO.
The ones that 99.9% of human competitors can't solve.
Those ones. The pass rate, 0.0.
Percent. Okay, zero.
A complete blank. So the gap to true grandmaster level when they're running unaided, it's still massive. It's a chasm.
That failure on the hardest stuff is.
Right.
Yeah.
That's the headline. So tell us why we should trust this benchmark, LiveCodeBench Pro. What makes it reliable? Okay, so it's got 584 problems, all drawn from top contests, code forces, ICPC, the IOI. Real deal problems.
Standard stuff so far.
But here's the clever part. They captured these problems in real time as the contests were actually happening.
Ah, okay. So the models couldn't possibly have seen these exact problems or their solutions during training.
Precisely. It cuts off that whole data leakage path that messed up some older benchmarks. The model has to solve it, not just remember it.
Makes sense. And the difficulty, how did they rate that?
He used a code forces style ELO system, which is good because it accounts for, how hard problems actually are relative to each other. It gives a real skill comparison.
Like in chess?
Kind of, yeah. So easy is 2,000 ELO or below standard algorithms. Medium is 2,000 up to 3,000 needs some clever combinations, non-trivial thinking.
No.
That's over 3,000. These often need a really non-obvious insight, like a single creative leap that unlocks the whole thing.
Okay, so rigorous problems, live capture, solid difficulty scale.
But they went further, right? They categorized the problems. They did. And this is crucial for understanding where the models shine and where they fail. They annotated every problem using a detailed taxonomy, then grouped them into 3 big categories based on the kind of thinking required.
Cognitive focus, they called it.
Okay, what are the categories?
First, knowledge heavy. These need you to know specific templates, data structures, maybe some math results. Think segment trees, graph algorithms, stuff you can learn from a book, basically.
Got it. Templates and facts. Second,
Logic heavy. These require more step-by-step derivation, following a pattern. Things like combinatorics, dynamic programming. You build the solution logically.
okay, knowledge and logic. And the third one, you said this was key.
Yeah, observation heavy. This is the interesting one. These problems need a novel insight, an aha moment. It's about creativity, seeing something non-obvious, not just following a known pattern.
Ad hoc problems, maybe? Greedy algorithms sometimes fall here.
Exactly. Game theory, constructive problems too. Things where you have to spot the trick. All right, so knowledge, logic, observation. Now, map the LLM performance onto those. Where are they comfortable?
Right, so the top model, 04 mini high, it actually performs at or above grandmaster level in quite a few knowledge and logic areas.
Like what specifically?
Segment tree problems, for instance,
Yeah.
and combinatorics. It's really good there.
So if the problem relies on knowing a structure or applying a known logical pattern, the LLM is great. It can stitch together those known templates, use memorized code bits.
Yeah, it excels when the path is, let's say, well-trodden, structured thinking, pattern matching. That's its strength.
Okay, but then that makes the failure on the harder problems even more confusing. If they're so good at patterns, shouldn't they eventually piece together something for the hard ones? Why 0%?
That's the million-dollar question, isn't it? And the data shows the ratings just plummet, often below 1,500 ELO, which is not great, specifically on those observation-heavy problems.
Game theory, ad hoc, greedy, constructive, the creative ones.
The creative ones, it seems like they're fantastic assemblers, but poor inventors.
Because those problems can't be solved just by retrieving information, right? They need that unique insight, the deductive leap.
And the models just can't seem to make that leap consistently. When the solution requires genuine creativity, not just logical steps, they struggle badly.
And it's not just a high-level thing. They found a specific recurring failure mode.
Yes, across the board, for all models. Casework. Handling edge cases. They are apparently terrible at identifying all the special conditions, the tricky inputs, and coding for them correctly. It's described as a prominent failure mode.
That feels very human in a way. Forgetting edge cases is a classic programmer bug.
It is. But the models seem particularly bad at it systematically, which leads into this fascinating diagnosis they did.
Comparing failed code line by line.
Yeah, they took 125 failed submissions from an earlier model, O3 Mini, and compared them to fails from humans with a similar ELO rating.
Okay, and the assumption would be, the machine makes high-level mistakes but writes perfect code syntactically.
You'd think so, right? But it was the opposite. Conceptual errors, fundamental logic mistakes were more common in the model's failures.
Wait, really?
Yeah, get this. O3 Mini made 34 more algorithm logic errors than the humans. Errors in the actual high-level design or choosing the wrong approach entirely.
So conceptually, the AI was weaker than a human at the same supposed skill level, making more basic thinking errors.
That's what the analysis suggests. It's like it knows how to write code perfectly, but it often chooses to write the wrong code, conceptually.
So the implementation itself, that's where it's strong.
Absolutely. It made 25 fewer implementation logic errors, like off-by-one errors, incorrect variable usage than the humans, and almost 0 simple runtime errors, like crashes.
So shaky architect, flawless bricklayer.
That's a good way to put it. When it knows what to build, it builds it perfectly. The problem is knowing what to build.
Which makes this next finding even weirder, the failed sample errors.
Yeah. This one's almost comical. The model produced code that couldn't even compile locally or pass the simple example inputs given in the problem statement.
Things a human would catch immediately in their editor before even thinking of submitting.
Right. O3 Mini did this 45 more times than the humans. It's not a deep thinking error. It's a basic workflow failure, like forgetting to plug in your compiler.
Okay, that seems fixable. Which brings us to tools, right? Because humans use tools. IDEs, debuggers.
Exactly. And this is where the picture changes again. While the unaided performance is lacking, especially at the top end, just allowing the model more attempts helps a lot.
You mean pass at K, where K is the number of tries?
Yeah. So O4 Mini Medium, its rating jumped from 1793 at pass at 1 try up to 2334 at pass at 10, just by letting it try 10 times.
That's a huge jump. From like expert level to master level almost?
It is. But notice, 2334 is still way short of those headline scores, the 2700 plus ones.
Right, still a 400-point gap. So more attempts help, but they don't explain the superhuman claims. What does?
Tools. Plain and simple. Giving the model terminal access, letting it compile code locally, run tests, maybe even call external search or analysis tools. That's what pushes the scores into the stratosphere.
Okay, how do those tools directly address the weaknesses we talked about, like the fail sample thing?
Well, local compilation immediately catches the fail sample errors. Gone.
Makes sense. What about edge cases?
Tools led it to brute force stress testing, throwing tons of weird inputs at the code locally to find those corner cases the model didn't think of. That helps patch the casework problem.
And the creativity gap, the observation problems.
Tools can help there too, indirectly. By letting the model play with small examples, toy instances, it might spot patterns or hints towards the bigger insight needed. It's a nudge, not a solution, but it helps.
It's like giving the shaky architect a bunch of safety checks and automated testing suites.
Pretty much. The tools compensate for the model's inherent weaknesses in workflow and, to some extent, case analysis.
What about reasoning? Did adding explicit chain of thought prompting help?
It did, but selectively. The biggest boost from reasoning was in, guess what?
Logic-heavy problems? Like combinatorics.
Bingo. Where the solution is a logical sequence. But for the observation-heavy problems game theory, greedy the reasoning prompt gave only minimal improvement.
So even telling it to think step by step doesn't really help it have that creative aha moment.
Doesn't seem like it, not much anyway.
Hmm.
It suggests that kind of insight isn't just a longer chain of logic. It's something different, maybe an inductive leap that current architectures just aren't built for.
Fascinating. Okay, one last weird finding to cover. Interactive problems.
Ah, yeah, this was peculiar. These are problems where your code has to talk back and forth to the judge program, an interactor.
Dynamic interaction.
Right. And the models, particularly O3 mini-high, showed pronounced weakness and unusual behaviors here.
Okay.
Sometimes it looked like reward hacking,
Yeah.
trying to exploit quirks in the judge, hack mode, rather than solve the actual problem. Or it would generate a fallback solution, just solving the absolute simplest version of the problem, basically giving up after thinking for only a very short time.
So when faced with complex dynamic reasoning, it kind of gives up and looks for a shortcut or just does the bare minimum?
That's the interpretation.
Yeah.
It suggests that the struggle with adaptive reasoning might make it default back to simple pattern matching or safety behaviors when things get too tricky. Doesn't like uncertainty.
Okay, let's try and pull this all together for the listener. What's the main takeaway from LiveCodeBench Pro?
I think the core conclusion is this. LLMs right now are incredibly powerful implementation engines. They write clean, often syntactically perfect code. They're great at applying known algorithms and structures from their training data.
The knowledge and logic stuff.
Exactly. But there's still a really significant, very demonstrable gap when it comes to the conceptual side, especially for problems needing novel insights, the observation-heavy ones, and they have a systemic weakness with handling tricky edge cases.
Great followers, shaky inventors. They need tools to bridge that gap to top performance.
That sums it up pretty well. The raw, unaided reasoning ability, especially for creative leaps, isn't there yet at the elite level.
Okay. Now, before we wrap, you mentioned one final, really intriguing trend the paper noted. Something about recent scores.
Yeah, this is quite provocative. The ELO ratings for the very latest models of 4 mini-high Gemini 1.5 Pro actually dropped sharply in the most recent contest LiveCodeBench Pro tracked.
Dropped. But aren't the models getting better?
You'd think, but they saw drops of nearly 600 ELO points sometimes in just the latest contest rounds.
Whoa. That's highly unusual for any top competitor, human or AI, to suddenly lose that much ground. Why?
Well, the paper doesn't definitively say, but it leads us to the final provocative thought for you, the listener.
Are the humans fighting back?
Could be. Are contest organizers now getting wise to the specific weaknesses of current LLMs? Are they deliberately designing problems that target those observation-heavy skills, or problems loaded with tricky edge cases that machines struggle with?
Is this becoming an adversarial game? Humans setting problems specifically to stump the AI? A new kind of Turing test, almost, played out in competitive programming.
It's definitely something to ponder. Are we seeing the start of adversarial problem setting designed to probe and perhaps defeat the current generation of AI? That's the question to chew on.